Hello, everyone. My name is Lisa Lin. I'm from the University of Illinois Urbana-Champaign, and I'm pleased to share our recent work accepted by ICCV 2025. Its title is Anti-Tamper Protection for Unauthorized Individual Image Generation. Individual image generation is about using people's own image to customize the generation results. Currently, lots of companies provide service to support the personalized generation for the users. However, the service can also be misused and have the potential to infringe the image owner's privacy or portrait right. As a result, researchers propose the protection perturbation, which is embedded inside the image and can interfere with the generation process, leading to degraded image quality. However, an attacker can leverage purification algorithms to remove the perturbation. As a result, in this project, we propose an anti-tamper perturbation, which is the first work to explore a tamper-proofing mechanism of the protection perturbation. The key idea is to let the service provider can detect if the protected image has been tampered with purification and reject unauthorized generation requests accordingly. We abbreviate anti-tamper perturbation as ATP. It consists of two components. One is protection perturbation. It functions to disturb the generation process. Another is the authorization perturbation, which encodes an authorization message into the image. When purification occurs, the integrity of this message is disrupted. Then, the service provider can detect the tampering. One challenge of designing such mechanism is the authorization perturbation must remain intact despite changes induced by protection perturbation. Another is that we need authorization perturbation to be vulnerable enough to be erased by purification. These two challenges seem to be conflict. We handle these challenges by moving the image to the frequency domain and embed the two perturbations in different frequency bands so they don't interfere with each other. And in the frequency domain, each coefficients are influenced by many pixels, which makes the authorization perturbation sensitive to the purification. Specifically, we designed an ATP pipeline. The image is first transformed into the frequency domain. We then prepare a binary string as the authorization message. This message is embedded into the image's frequency domain under the guidance of a binary mask and can later be verified by a message decoder. We introduced the improved frequency domain PGD algorithm to embed protection perturbations into the frequency domain under the guidance of a mask. Similar to other PGD-based algorithms, it is designed to maximize diffusion loss. The unique part is it alters the frequency coefficient according to a guiding mask. The gradients to the frequency coefficient are calculated and masked to control the region used to do protection perturbation. Then frequency coefficients are updated by a PDD step. We iteratively update the image according to the algorithm. As other protection perturbation algorithms are all based on PGD, it allows ATP to leverage any existing protection perturbation algorithm to generate its protection component. With the method in place, we then move on to the experiments. We evaluate our approach on two popular face benchmarks, and we perform generation with Dream Booth. The protection performance is evaluated on the generated images from two perspectives: image quality and the identity consistency. We use protection success rate to evaluate how ATP works when the purifications are applied. First, we check the authorization message. If the bit error exceeds a threshold, that means the tamper-proofing was triggered, and we count it as protected. If not, we fall back on a clip IQAC threshold to decide whether the generated image still preserves protection. We select four protection perturbation algorithms as baselines and adapt them to ATP. From the figure, we find that under the clean conditions, all methods maintain relatively high protection success rates. However, after the application of purification, all baselines suffered from an unavoidable decline. In contrast, Incorporating ATP enables baseline method to reach a 100% protection success rate due to the success of tamper-proofing mechanism. We also do experiment to check how does the ATP work on the attack without purification. In this case, the tamper-proofing mechanism will not be triggered. From the quantitative results, we see ATP performs comparable to the original baseline. From the visual result, we can see that each baseline still effectively degrades image quality after being adapted to ATP. Next, we use the ablation study to understand which parts of ATP actually matters. In this table, we compare different design traces. We find that the mask-guided fusion of authorization and protection perturbations is essential. Frequency domain perturbation better conceals the authorization message, and the improved PTD is crucial for ensuring that the protection perturbation aligns properly with the mask. We also compare ATP sensitivity on the different type and levels of purification. Once purification is applied, frequency domain ATP is sensitive. The bit error increases faster than in pixel ATP or phase signs. Finally, I'm going to summarize the key points of this project. We find that the purification attacks can easily bypass existing protection methods. As a result, we propose anti-tamper perturbation introduces tamper-proofing mechanism into the perturbation. Facing attack with purification, ATP enhances all protection to achieve 100% protect success rate, confirming the effectiveness of its tamper-proofing mechanism. Facing attack without purification, ATP behaves as a common perturbation but preserves normal performance. Thanks for watching, and we are welcome to the question.